morning. We are finishing our introductory study of vector spaces. So, coordinates. So remember, vector spaces have a basis, right? And what's a basis? And what does it mean for a set to span? Right, so every vector in space is a linear combination of your vectors in the set, spanning set, right? All right, so let this set be a basis for your vector space. It means for every single vector in your vector space V, you can write it this way. What do we know about each of the C's? So what are the C's? They're real numbers, and what else do we know about them? Can C1 be a different value? Can you have multiple values for C1? You have multiple values for C2? So they're unique. Each vector has a unique set of constants that would make this true. For this given basis. If I have a different basis, then your C's will be different, but they'll be unique for that basis. Well, then those C's describe this vector V for that given basis. Those are the coordinates of the vector with respect to the basis. And the vector of those constants is called your coordinate vector. Well, the idea is you're given coordinates for a specific basis. You can actually use that to determine the coordinates for a different basis. In other words, you can change your basis. You can form what's called a change of basis matrix. You have two bases for a vector space. There is a unique n by n matrix P, such that the coordinate vector with respect to C is equal to P times the coordinate vector with respect to B. And that matrix P is your change of basis matrix. How do you think you're going to find that change of basis matrix? What operation we're going to have to use? What do you think? Which is what? Yeah, we're going to row reduce a matrix. Big surprise. Self-augmented matrix. Left of the augment, each column of the matrix is a vector in the basis you want to convert to. To the right of the augment is the basis that you're converting from. Row reduce that. You'll get the identity matrix augmented with your change of basis. So more row reduction. That's what I'm saying. If you row reduce a matrix, You're definitely on the right track. Of course, the question is, did you reproduce the right matrix? So yeah, you can just pass looking out just by knowing how to reproduce a matrix. Right, so instead of a 2-vector, AB, and the basis, 1, 1, 2, 3, and we'll use this to find the coordinate vector for 4, negative 3. I guess the first thing we should do is actually verify that that is a basis. Let's actually do that. What vector space are we working in? What do you think? You think the vector space is?
Should be pretty obvious. R2.
R2, right? So let's just first verify that this actually is a basis. If it's not a basis, then it wouldn't make sense to try and find a coordinate vector. That's just going to work out really nicely. We're doing a lot of stuff. One simple step. Now, since I'm verifying, let's do this by hand. We haven't done row reduction by hand in a while. Negative row 1 plus row 2, right? Then what? Who remembers?
-2 row 2 plus 1.
And make 2 row 2 plus row 1. A real nice simple matrix to reproduce. And that is what you should get. that row reduction shows that B definitely spans R2. If you just set A and B to be 0, it shows that you only get one solution, right? The trivial solution. Which shows linear independence. That's the definition of a basis. Yay. We're happy. Oh, by the way, I just found my coordinate vector. C1 is negative, would be 3A minus 2B, right? C2 would be negative A plus B. So there's our coordinate vector. V. Then the coordinate vector with respect to the basis, 3A minus 2B, negative A plus B. U was the vector for negative 3. What is the coordinate vector for U with respect to this basis? I shouldn't be calculating for this. What was it? I agree, it's 18. How'd you get it? Yeah. You guess? Should it be? Or is? It is 100%. That would be a coordinate vector. All right, since we already found the coordinate vector for any generic 2 vector, just plug in 4 for A, negative 3 for B, solve. 18, negative 7. Right. So those would be the coordinates for this vector space with the given basis. Well, the coordinates in space, x, y, z, that would just be R3 with respect to the standard basis, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. So at least when we're talking about standard vectors, these will give us coordinates with respect to different ways of drawing the axes. Right, in this case, base is 1, 1, 2, 3, so you have to draw the vector 1, 1 as your x axis, right? The vector 2, 3 would be your y axis. Then your coordinate in that axis system would be 18, negative 7. Before negative 3, right? That's how it would kind of transform, so to speak. This would allow us to kind of like visualize vector spaces as coordinate systems. So we do some geometric stuff on it, which I'm not going to do because I hate geometry. Find coordinate vector relative to both standard basis E and that set, that basis. No. You shouldn't require any work. What's the coordinate vector with respect to the standard basis? ABC. You just lost 40 points for being a song stuck in my head. It's going to be a lot worse if my kids are hearing them singing all the time. Setting up with you. First, let's again do the same thing we did before. Let's actually verify that that does indeed form a basis for R3. What is the augmented matrix we're going to be setting up?
Wouldn't be the two vectors we already see augmenting the vacancy.
So I'll give you the actual matrix.
So it would be going from top to the bottom of 1, 1, 1, A. Or yeah, no.
Right, you're going row column.
We'll go by columns since you've already started. Next one would be 1, 1, 0. Then 1, 0, 0. Augmented with A, B, C.
Good, we didn't sing it this time. Oh, so you're not saying just to suck up, but another 30 points off. Can never win. House always wins. All right, so we'll reduce that. Tell me what you get.
An immediate problem.
I'll let you use your calculator. I'll be nice. As long as it has some Bob manipulation, so it's a CAS. Yes. Remember I showed it all in class.
I have already.
Go ahead. Are you gonna go by column or row?
Oh, yeah. 1, 0, 0, C, 0, 1, 0, B minus C, 0, 0, 1, A minus B.
I agree. So, quick comment. I'll say that you had no problem with that. Make sure that you don't have A, B, C stored as a value. Otherwise, it's going to use those values in the matrix. Easy way to tell if you have something stored, is it bold? If the letter comes up bold, that means it has a value stored to it. So you have to clear it out. And that's not difficult to do. You just go into document settings, scroll all the way down, clear. So this shows that it does span, right? Right, we have a solution for C1, C2, C3. If you set A, B, and C to all be 0, and that would be the 0 vector, do you get anything other than the trivial solution based on this row reduction? No. So it would show C1 is 0, C2 is 0 minus 0, C3 is 0 minus 0. So it's linearly independent as well. So it is indeed a basis. Good. What's the coordinate vector with respect to B?
It would just be C, B minus C.
Yeah, and it's just that augment, right? And there's your coordinate vector. Well, they didn't ask, but let's find the change of basis matrix or the transition matrix. Let's go from the standard basis to C. Or to B. So that's typically written, it will be typically written this way. Right, to represent we're going from E to B. So remember to do that. We're all setting up an augmented matrix. Left of the augment, You use the vectors from the basis that you want to convert to, which in this case would be B. Augmented with now, you use the vectors from the basis you're converting from, which for us is E, the standard basis. You row reduce that. You will get the identity matrix, then augmented with A. Let's bring that up. So we got. That would be the change of basis matrix. From E to B. Right. Which means you're given the coordinates for a vector with respect to the standard basis E, which is actually very easy to do. If you wanted your coordinates with respect to the basis B, you would now take that matrix you just found, and multiply by the coordinate vector with respect to A. Verify that. Do that product. you should get that. And you're going to verify is that you get that product. Does that give you C, B minus C, and A minus B? It does. You shouldn't actually be calculated for that. Row by column, right? When you multiply 0 times A plus 0 times B plus 1 times C. That's C, right? 0 times A plus 1 times B plus negative 1 times C. Is that B minus C? Yes. 1 times A plus negative 1 times B plus 0 times C. Is that A minus B? Yes. Verified. First, we're going to show that this set forms a basis for P3. What is P3? This will also show me who actually watches the videos that I post, because I defined it to fit on the very first video on vector spaces. P3 is a vector space. Which vector space is it? Oh, you think it's that. Huh? Might have been. It might be in the textbook.
Yeah, I'm trying to remember.
It's the vector space of all polynomials degree 3 or less. What's the dimension of P3? And how you got 3? You forgot the term. You forgot the constant term. Right, because degree 0 is also in there. So you get 0, 1, 2, 3, that's 4. Yeah, you have to count 0. Yeah. Right, if you start at 0, then 0 has to be counted as 1. Let's see who's good at algebra. Without writing anything down and without using a calculator, expand out t minus 1 to the third power. Oh, it took you too long. Pascal's triangle, it's a beautiful thing. Row 3, Pascal's triangle, 1, 3, 3, 1. Those are your coefficients. T cubed minus 3 times t squared times negative 1. Then plus 3 times t to the first power times negative 1 squared. Plus 1 times negative 1 cubed. T minus 1 quantity squared. Again, took too long.
T squared minus 2t plus 2 plus 1.
Plus 1. You're gonna need those. Still think about Pascal's. One, 5. Yeah, it's 1, 5, 10, 10, 5, 1.
Is that an alternating pattern between t minus 1 cubed and t minus 1 squared? Where like it's like minus 3t squared and then t squared. It's like negative and positive, and then the next.
Because it's a minus 1, yes.
Okay.
Your signs are going to alternate because of that.
Yeah.
But what it really boils down to is it's binomial theorem. I'll just leave that there, that's fine. Says if you take x plus y, raise it to the nth power for any integer n, and you can actually extend the binomial theorem to, I believe, rational numbers and negatives using series. Taylor series in particular, it's an application of Taylor series. That's the binomial theorem. Where n choose I is a binomial number, which is easiest found by Pascal's triangle. Right, so that's what I said. The third row of Pascal's triangle, which is what I need here because n is 3, 1, 3, 3, 1. So 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. And then it's just x to the n minus 1, right? So start x cubed, that reduces by 1 each time. In this case, it was t. Negative 1 starts at 0, and that power increases by 1. That's why it's alternating.
Okay.
Because negative 1 to 0 is positive, so the first is negative, squared is positive, cubed is negative, so on and so forth. All right, so we're showing that this forms a basis. Let V be any arbitrary vector in P3. What would a vector in P3 have to look like? So what does a generic polynomial degree 3 or less look like? This is from pre-calc. Actually, maybe before that. Algebra 1, you looked at polynomials. Algebra 1 was 3 years. You skipped a lot. Algebra should have way more than 3 years ago at this stage.
Yeah, that's fine.
Probably that way. Remember that? AT cubed plus BT squared plus CT plus D. A, B, C, and D are just real numbers. And that's just a standard polynomial degree 3 or less. If I want it to be degree 3, I have to restrict A to be non-zero. Let's solve that equation. Now remember, span. For this set to span P3, there has to be a solution to that equation. You should probably have an apostrophe there. English is hard. What did I misspell?
You misspelled this one, but then you don't worry about it.
No, I'm gonna work, so I'm gonna fix it.
There it is.
Oh, right there. Reese. Reese.
You can probably guess like something to say with it, really. Kind of must have been.
It's a math word. English is hard. That's why I'm not an English major. Well, this equation would be this. Right? And then gather all of your like terms together. In this case, I'm actually just looking at, I'm doing like terms in terms of the t cubes and all that. For t cubed, there's only a 1. T squared, negative 3c1 plus c2. T, 3c1 minus 2c2 plus c3. Then negative c1 plus c2 minus c3 plus c4. That's equal that. And then you do coefficient comparison, right? Coefficients for t cubed have to equal. Coefficients for t squared have to equal. Coefficients for t have to equal, and coefficients of the constant have to equal. This is a simple system to solve, so I'm starting to set it up as a matrix. C1 has to equal A. Negative 3C1 plus C2 has to equal B. 3C1 minus 2C2 plus C3 has to equal C. And finally, negative C1 plus C2 minus C3 plus C4 has to equal B. Now, I want you to look at that. What do you notice about column 1? Right, more specifically, it's the coefficients in your first vector, right, your first column. What about second column? Same thing, isn't it? It's the coefficients. Coefficients. Specifically, these are actually your coordinates with respect to the standard basis. I'd be able to skip all that from this point on. All right, let's reduce that. You should get that. Does that system have a solution? Right, so is the system consistent? Yes. So that's implying now S spans P3. What happens if A, B, C, and D are all 0? Which would be the zero column, which is the identity for P3, right? What does that matrix say? Is it linearly independent? If A, B, C, and D are all 0? Yeah, it's linearly independent, right? You get only trivial solution. C1 has to be 0, C2 has to be 0, C3 has to be 0, C4 has to be 0. the basis for P3. Find the coordinate vector for 3t cubed minus 4t squared plus 2t minus 5. First of all, how many coordinates should you have?
4.
Now tell me the coordinate vector. What's the first coordinate? That's an easy one. What is it? That's not a coordinate. Just 3.
Oh, great.
What's the second coordinate? Five. Third coordinate. And the fourth coordinate. There's the coordinate vector.
How did you find that?
How did you find them? This here would be your coordinate vector for an arbitrary AT cubed plus BT squared plus CT plus D, right? What was A? What's B? What's C? And what is D? Plug them in. Because really what you're doing is plugging in here and then row reducing it. Which just has the same effect of just plugging in here, right? What vector space are we working in? This is the vector space M22. Set of all 2 by 2 matrices under standard addition and scalar multiplication. What's the dimension? Four. 2 rows by 2 columns. 2 times 2, 4. Standard basis. Is that? So we want the coordinate vector for that 2 by 2 matrix. Which was 2, 4, 7. Means we want to find the constants that make this true. Oh, that's easy. What are the coordinates? That was easy. It's always easy with the standard basis. But now they want it with respect to that basis there. And that is a basis. I'll let you verify that on your own. Well, using the notion of coordinate vectors, there's the coordinate vector for your first matrix in the set. For the second, for the third, and the fourth. Now, rather than having to go through that entire headache of writing out the system of equations again, I can just jump right to using coordinates with respect to the standard basis. Row reduce that matrix. You already know you're going to get the identity matrix because it's a basis. That will be augmented with the sake of time. Sorry. What is our coordinate vector then of A with respect to this basis B? What's our coordinate vector? Which is what? Here's your coordinate vector. So again, it's just more of this RR again. I'll let you do that one. But the idea is to use the coordinates that we just went over. Makes this a lot easier. Whatever. English is hard.
Oh my God.
English is hard. So I have to add something in here. Actually, I have to mention a few things. Not having a good day on Tuesday, and this there is a homework on rank and nullity. I wrote homeworks for linear transformations, and one of those didn't have a homework. That's what I was thinking of. So that homework is due April 1st. April Fool's Day, my favorite day of the year. I really conserve my life with fake divorce papers. Project 3 is also due the 1st. Third quiz is now available. That will also be due the 1st. And the second exam is actually next week. So I also misspoke on that. So the second exam is next Thursday. So that will cover everything up through what we do on Tuesday, which is the start of linear transformation. Have a good weekend. I don't know if people will be. Well, I can know this one.